Alright guys, so as promised, we're going to be looking at the limit as x goes to c of sine of x. And throughout this entire video, or maybe a series of videos, depending on how long this takes, we're going to show that this is equal to sine of c for any value c in the domain of sine, which essentially means that c can be any real number. But to start out, because of the nature of how we're doing this, and because we're going to be using that arcsine function, which only takes in values from -1 and 1, and also has some other sort of weird properties, we are going to limit our c values for now to be less than pi over 2 and greater than -pi/2. And this video / series of videos is going to be applying a lot of the concepts we've been using in previous proofs. So, but if you just pay attention, get through it, hopefully it should all make sense. So what we have to show is that for any epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of sine of x minus sine of c is going to be less than epsilon. Okay, so let's take a look at what this means. It means that if we pick an x value such that the absolute value of x minus c is less than delta, but greater than 0, so we can actually draw out what these x values are. It would look something like this. We're talking about x values from c minus delta to c plus delta, not including x equals c itself. If we were to pick any of those x values, then we have to show that the absolute value of sine of x minus sine of c is going to be less than epsilon. So for any epsilon greater than 0, we have to show that that delta exists, such that if we pick an x value from c minus delta to c plus delta, not including x equals c, then the absolute value of sine of x minus sine of c will be less than epsilon. That is our goal. We're going to do that by actually showing that we can pick any x value from c minus delta to c plus delta, including c itself. Because if we're to show that, then we've still shown that all those x values excluding x equals c will still yield the absolute value of sine of x minus sine of c values that are less than epsilon. So what we're going to actually show is that for all the x values that are the x minus c values that are less than delta but greater than negative delta. And that's that same interval, just including x equals c. And now we're going to do some algebra here to figure out sort of what does this inequality imply. So I'm going to rewrite this because it's an absolute value. We have the ability to do this, split this up into 3 separate expressions. And what I'm going to do now is I'm going to go ahead and I'm going to solve for x. So I'm going to add sine c to each part. That leaves me with x, or sine of x. So we're going to add sine c to each part. The next thing I'm going to do is I'm going to take the arcsine, or the inverse sine. I'm going to write it as arcsine, just so we don't get confused with that little -1 on the top. But I'm going to write it as arcsine. I'm going to take the arcsine of each component. And this is where we hit our first problem. It's not really a problem, pretty easy to solve, but as you guys know, arcsine can only take in values that are greater than -1 but less than 1. So there's a very specific domain that arcsine can function in, and that means we have to restrict what our epsilon values can be. So our epsilon value has to be less than, in this case for right here, because we don't want this value to go below -1, it has to be less than sine c plus 1. We cannot have an epsilon value greater than that for this proof. And you might be asking, well, we have to show this for any epsilon value. For now, we're going to show it for specific epsilon values and then extend it. So epsilon has to be less than sine c plus 1, and here epsilon is going to have to be less than 1 minus sine c. And by being less than that, this is going to prevent this term from that's inside this arcsine from being greater than 1. So we've placed 2 restrictions on our epsilon value, it has to meet both of them. So epsilon has to be less than sine c plus 1 and 1 minus sine c. And I'm going to go ahead and I'm going to say epsilon 1 is equal to sine c plus 1. And I'm going to say epsilon 2, these are just two variables, or not really variables, they're constants, because I'm setting them equal to these two things. They do depend on c, so they can change. So epsilon 1 equals this, epsilon 2 equals this, and I'm going to say epsilon naught is equal to the minimum of epsilon 1 and epsilon 2. And what I'm going to show is that for any epsilon greater than 0, but less than epsilon naught. So I'm picking for any epsilon value greater than 0, but less than the minimum of these two. And if I'm less than the minimum of these two, I know I'm less than both of them. So that's how I'm going to limit my epsilon values to make sure that this arcsine function here still works. And now I'm going to go back. So let's just draw a little dotted line around this so we know we just had to take care of that little hitch. And we're going to subtract c from each expression here to get something that looks like this. Arcsine of sine of c minus epsilon minus c is going to be less than x minus c, which is going to be less than arcsine of sine c plus epsilon minus c. And that looks pretty crazy, but it is important. We're going to be using it. And I'm going to go ahead and erase what's up here and write that final expression that we just got right over here. That arcsine of sine of c minus epsilon minus c is going to have to be less than x minus c. It have to be less than the arcsine of sine of c plus epsilon minus c. And the whole reason for doing that is now we know, let's rewrite this, 1 minus sine of c. Now we know that if we're to pick an x value such that x minus c is greater than this term but less than this term, then epsilon will be greater than the absolute value of x minus, greater than the absolute value of the sine of x minus sine of c. So if we're to show that for our x values this statement is true, then this epsilon statement will still be true. Now I'm going to take the next step. This is what we've done in multiple proofs. First, what is important to recognize is that this number here is always a negative number. You can prove that if you want. Just set it to be set it to be less than 0, and you'll eventually end up coming out with epsilon greater than 0 to let you know that that's true. And you can do the same here. This number will always be a positive number. That's just based on the constraints we have set. This will always be positive. This will always be negative. So I'm going to go ahead and say delta 1 is equal to the negative of this, because we know whatever delta value we're going to end up picking has to be positive. C minus arcsine of sine of c minus epsilon. And I'm going to say delta 2 is going to equal arcsine of sine of c plus epsilon minus c. And this is actually why we had to limit our c values to this specific range. If we didn't do that, we would be able to come up with delta 1 and delta 2 values that were negative, and we know we can't have that. So this proof that I'm doing right now only works when c is in this range. Again, we'll extend it later. But if you take a look at what delta 1 and delta 2 equal, we can rewrite this inequality right here as negative delta 1 is less than x minus c, which is less than delta 2. So we know that whenever this inequality is true, epsilon will be greater than the absolute value of sine of x minus sine of c. Well, what does this look like? What x values does that correspond to? And we definitely are going to have an idea of what that looks like. It's going to be c plus delta 2, and c minus delta 1. And delta 1 and delta 2 will not be the same size. But now we know that if we pick x values inside this interval between delta 1 and delta 2, we will get back sine of x minus sine of c values, the absolute value of that are less than epsilon. And that's what's important. That's what's going to let us pick our delta value. Because any x values inside this interval satisfy this inequality. So what we're going to do is we're going to say delta now. Delta is going to equal the smaller of the two. And remember, when I do this, delta equals minimum, you might be wondering, well, how do you know which one's smaller? How do you know which delta is smaller? How do you know which epsilon is smaller? Sometimes you can figure it out, but it's not actually necessary to figure out. All we have to know is that that epsilon value, or that delta value, specifically in this case, we know it exists, and that's all we care about. We just have to show that it exists. So delta is going to be the minimum of those two, and what ends up happening is if we define our c to c plus delta and c minus delta, now all the values in here are also in this interval with delta 1 and delta 2. This interval right here will be a subset of this one, because let's say delta 2 was bigger, just for the sake of argument. Then maybe all the x values all the way up to delta 2 worked, but that means the ones that stopped right here all the way up to here still worked as well. So if delta 2 is out here, all the values up to delta 1 length this way, a delta 1 length this way, will still make it so this inequality holds. So by picking that minimum delta value, we've defined a range of x values around c such that when we plug in those x values into this equation right here, the absolute value of sine of x minus sine of c will be less than epsilon. So we have shown that for any epsilon value greater than 0 but less than epsilon naught, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of sine of x minus sine of c will be less than epsilon. And that delta value is going to be the minimum of these two. And now this is where you might start asking, what about epsilon values greater than epsilon naught? I thought you had to show this for all epsilon values, and you're completely correct. I do have to show for all epsilon values. But here is the key. So I'm going to go ahead and erase this to make some space. But I'll keep this delta statement because it's important. So delta is equal to the minimum of delta 1 and delta 2. The reason that my proof still works and that I can show that for any epsilon value there is a delta value is because if we were to look at a mock graph of the sine function at negative pi over 2 to pi over 2, and this is true for any function, not just the sine function, but I'm going to start at negative 1, work my way up to 0. We know this is what the sine function looks like on that interval. What I'm saying is at c, the limit is equal to L. If you're to give me an epsilon value, perhaps up to about here and down to about here, where this is L plus epsilon and this is L minus epsilon, and this right here is going to be c minus delta, and this is going to be c plus delta, I'll find you that delta value. And I'll find it all the way up to epsilon naught. I can actually give you that exact value. And you might be wondering, well, what if I give you an epsilon value that's bigger than that? What if I give you an epsilon value all the way up here? So this is L plus epsilon, and you just gave me, let's call it epsilon 1, and L minus epsilon 1. Well, the thing is, I can just use my exact same delta value as before. Because if this delta value was to give me back all sine of x values that fell in a range of that smaller epsilon value you had at first around L, then they'll still give me those same values, and those values will still fall in a range around L of that size of the bigger epsilon value. Because this interval right here, it will essentially define the smaller interval will be a subset of that bigger one. And you can kind of see that on this graph, is now I could pick a delta value that can give me f of x values all the way from the top to the bottom, all the way from here to here. But if I just pick that old delta value, I'll still only get back f of x values in this tiny interval, and they'll definitely be inside that bigger interval. So by putting a limiting case on my epsilon where it has to be less than some number, it doesn't really matter. If you were to give me an epsilon bigger than epsilon sub 0, I would just pick a delta value that I found for some epsilon that's less than epsilon sub 0, and it would still work. And if you were to give me an epsilon less than epsilon sub 0, then I just pick the minimum of delta 1 and delta 2 based on that situation. So I've shown that for any epsilon greater than 0, even getting rid of this case, that there is a delta greater than 0, such that if 0 is less than x minus c is less than delta, then the absolute value of sine of x minus sine of c is less than epsilon. And that is specifically when c is greater than negative pi over 2 but less than pi over 2. Now we're going to go ahead and try and expand that and make it so that it's true at pi over 2 and negative pi over 2 as well. All right, so we're going to continue on. Now we're trying to prove that the limit as x goes to c of sine of x is equal to sine of c, specifically when c is equal to pi over 2. So we're going to look at that case first. So we're looking at the limit as x approaches pi over 2 of sine of x is going to equal the sine of pi over 2, which is just 1. And the way we have to do this, because of the nature of that arcsine function, is by evaluating a left-hand and a right-hand limit separately, which is very tedious, but it is the only way, really, that we're able to do this because of that arcsine function. Otherwise, we're going to start getting some negative delta values that are not going to work out. So we're going to look at it from the left first. And if you don't remember the definition of this left-handed limit, please review that. We're going to try and show that this is equal to 1. So we have to show for any epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than, this is going to be c minus x, no absolute value because we're looking at that left-handed limit, which is going to be then in turn less than delta. Then f of x is sine of x, minus L, which is 1, will be less than epsilon. And we know c in this case is going to be pi over 2. So let's go ahead, let's try and prove this. We're going to mess around right here with this like we have done before. And we're just going to math through it, solve for x. We're going to get 1 minus epsilon, so less than sine of x. And we're going to get epsilon plus 1. Well, here's the thing. Epsilon has to be greater than 0, and sine of x only gives back values between -1 and 1. So we know epsilon plus 1 will always be greater than sine of x, no matter what value of x we put in. So we really only care to find out for what values of sine of x, or for what values of x will sine of x be greater than 1 minus epsilon. Because this statement right here will always hold to be true. So let's find that out. We get arcsine again of 1 minus epsilon. It's going to be less than x. And this lets us know something else important. If you guys remember with arcsine can only take in values from -1 to 1. So we have to say that epsilon is less than 2. So we're going to do this for any epsilon greater than 0, but epsilon's less than 2. We're going to go ahead and multiply both sides by -1, and that's going to flip the inequality and add pi over 2. So we get pi over 2 minus arcsine of 1 minus epsilon is going to be less than pi over 2 minus x. So whenever we pick x values, whenever we're picking x values that are such that pi over 2 minus x is less than pi over 2 minus the arcsine of 1 minus epsilon, then epsilon will be greater than the absolute value of sine of x minus 1. Well, that lets us know that if we set our delta equal to pi over 2 minus arcsine of 1 minus epsilon, then all the x values we pick will be such that pi over 2 minus x will be less than pi over 2 minus arcsine of 1 minus epsilon, and therefore epsilon will be greater than sine of x minus 1. And that's for any epsilon values. We can find that delta value. For any epsilon values greater than 0 but less than 2, we can find that delta value just by plugging in epsilon. And again, you might be wondering, well, we have to do this for any epsilon greater than 0, not just epsilons greater than 0 less than 2. But if you remember what we just did in our last proof, if we were given an epsilon that's greater than 2, if given epsilon greater than 2, we can find that delta just by picking a delta for epsilon less than 2. And we will have found that delta. And we explained that just a couple minutes ago. So review that if that didn't make sense. But when we're given an epsilon greater than 2, we just pick a delta that we would get for any epsilon value less than 2. And we still find the corresponding delta. So now we've shown that the limit as x goes to pi over 2 from the left of sine of x is equal to 1. Let's show that that same is true for the right. But we're going to do this in kind of a tricky way. And this is why we have to do these one-sided limits, because of that arcsine function and the way it behaves. We're going to look at the limit as x approaches pi over 2 from the right of sine of pi minus x, not just sine of x. So we're going to say this equals 1. And we're going to go ahead and let's try and prove it. So to show that, we have to show that for any epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than x minus c, and c in this case is pi over 2, this is a right-handed limit, no absolute values, is less than delta, then absolute value of sine of pi minus x minus 1 will be less than epsilon. So we have to find that delta. Well, I'm going to go through and do exactly what we did last time. It's going to be the exact same process. So we're going to have sine of pi minus x minus 1 is less than epsilon. We're going to add 1 to each side. Sine of pi minus x. Well, this statement right here is always true. Again, epsilon plus 1 will always be greater than sine of pi minus x, because sine of anything will return a value between negative 1 and 1. So we just have to find the cases where sine of pi minus x is going to be greater than 1 minus epsilon. So let's take arc sine of 1 minus epsilon and look at what we have to do again. Epsilon has to be less than 2. We can't let it be bigger than 2. Arc sine will not be able to take that input. And let's get that back on frame. It looks like that was getting a bit out of frame. So epsilon has to be less than 2. So arc sine of 1 minus epsilon has to be less than pi minus x. I'm going to add x to both sides and subtract arc sine of 1 minus epsilon for both sides. We get arc sine pi minus arc sine of 1 minus epsilon, and then we're going to go ahead and subtract pi over 2 from both sides. Pi over 2 minus arc sine of 1 minus epsilon. So that lets us know if we pick x values such that x minus pi over 2 is less than pi over 2 minus arc sine of 1 minus epsilon, then epsilon will be greater than the absolute value of sine of pi minus x minus 1. So if we set our delta value equal to pi minus 2 minus arc sine of 1 minus epsilon, it's very easy to see that that in fact does work. That limits us to picking x values that are such that those x values minus pi over 2 are indeed less than pi over 2 minus arc sine of 1 minus epsilon, meaning that those x values will give back sine of pi minus x minus 1 values, the absolute value of which will be less than epsilon. So effectively, we've found a delta for any epsilon greater than 0 but less than 2, such that when 0 is less than x minus pi over 2 is less than delta, then the absolute value of sine of pi minus x minus 1 is less than epsilon. And if you were to give me an epsilon value greater than 2, what do? I just pick a delta value that I would have found by plugging in an epsilon value that was less than 2. And that delta value will still work for epsilon values greater than 2. And that's something we've explained. So that lets me know that the limit as x goes to pi over 2 from the right of pi minus x is equal to 1. Well, we just showed in that last video that pi minus x is equal to sine of x. So this lets us know that the limit as x goes to pi over 2 from the right of sine of x is equal to 1. And since we have these two one-sided limits in agreement, remember if the two one-sided limits are equal, then the whole limit exists and it is equal to 1. So this is of sine of x is equal to 1, and that's what we wanted to prove. So we've gone ahead and proven that. So this statement still is true for when c is equal to pi over 2. Now let's see if we can prove it for when c is equal to negative pi over 2. So we're trying to prove that the limit as x goes to negative pi over 2 of sine of x is equal to 1. So let's go ahead and do that. We're going to look at the limit from the right again. X goes to negative pi over 2 from the right of sine of x, and we're going to say that this is equal to negative 1. And we want to show that this limit is equal to negative 1. So that shouldn't have been 1, it should have been negative 1. Why? We're plugging in, we're trying to say that it's equal to sine of c, and sine of negative pi over 2 is negative 1, not 1. So let's go ahead and do this and show that for any epsilon greater than 0, there exists a delta greater than 0 such that when 0 is less than x minus c, which is going to be minus pi over 2, so just plus pi over 2, is less than delta, then, and I'm going to go ahead, instead of writing with the absolute values, I'm just going to go ahead and write it how we have been. Then negative epsilon will be less than sine of x plus 1, which will be less than epsilon. And let's go ahead and do some math over here with this. Simplify this out. What does it tell us? And we see that sine of x is greater than 1 minus epsilon, and sine of x has to be less than epsilon minus 1. Well, one of these statements, oh, and this should be minus 1 minus epsilon. Well, sine of x will always be greater than minus 1 minus epsilon, because minus 1 minus epsilon is going to be less than negative 1. So we know that this part of the inequality is always true. We just have to find the x values such that sine of x is less than epsilon minus 1. So how can we do that? We're going to take the arc sine again. So x has to be less than the arc sine of epsilon minus 1. When does that happen? Well, first, let's take a look at this again. Epsilon has to be bigger than 2. Because if epsilon is not bigger than 2, if epsilon is not bigger than 2, then we get an input into this arc sine function that is not in the domain. So, and not bigger than 2, sorry. Epsilon actually has to be less than 2. So we're setting epsilon to be greater than 0, but less than 2. So in that case, let's go ahead and add pi over 2 to both sides. So we get x plus pi over 2 is less than pi over 2 plus arc sine of epsilon minus 1. And again, we can see, when is our proof going to work out? Well, it's going to work out when delta is equal to pi over 2 plus arc sine of epsilon minus 1. So if you give me any epsilon value greater than 0 but less than 2, if I was to pick an x value such that x plus pi over 2 is less than pi over 2 plus arc sine of epsilon minus 1, then of course epsilon will be greater than sine of x plus 1, and that will be greater than negative epsilon. So that shows that for any epsilon greater than 0 but less than 2, we have that delta. Again, if I was to get an epsilon value greater than 2, then all I have to do is pick one of the delta values I found for an epsilon less than 2, and that will still work. So we've proven the limit from the right. We're going to now try and prove that limit from the left. And then we'll be finished with proving these two endpoints. So we're going to try and prove that the limit as x approaches negative pi over 2 from the left of sine of pi plus x is equal to 1. And why are we doing sine of pi plus x instead of just x? Again, it's because of that arc sine function. We don't want to be getting negative deltas, and so far we haven't. So we have to use sine plus, or sine of pi plus x instead of using sine of x and then kind of manipulate it at the end. So let's just see how it ends up working out. We have to show for any epsilon greater than 0, there is a delta greater than 0 such that if 0 is less than, this is going to be c minus x, so minus pi over 2 is c minus x is less than delta, then, and I'm going to write it without the absolute values, negative epsilon has to be less than the sine of pi plus x, minus 1 has to be less than epsilon. And let's do the math we've been doing again. We get 1 minus epsilon is less than sine of pi plus x, which is going to be less than epsilon. And, epsilon plus 1. Well, this statement, again, is always true. Sine of pi plus x is always less than epsilon plus 1. Sine gives us back something between negative 1 and 1. So we just have to find those corresponding x values that make sine of pi plus x greater than 1 minus epsilon. And what are those x values? Those x values are going to be found when we take this arc sine, get less than pi plus x, and we are going to multiply both sides by negative 1, flipping the inequality. We get negative arc sine of 1, let's move that inequality over, 1 minus epsilon. We're flipping that inequality. And on this side, we get negative pi minus x. And one thing to recall again, epsilon has to be less than 2. Epsilon cannot be greater than 2 because that arcsine function cannot take an input outside of numbers between -1 and 1. And now we're going to go ahead and add pi over 2 to both sides. So we're going to get negative pi over 2 here, and we're going to get pi over 2 here minus that arcsine. And again, we end up with delta is equal to pi over 2 minus arcsine of 1 minus epsilon. So for any epsilon greater than 0 but less than 2, if we use a delta value of pi over 2 minus arcsine of 1 minus epsilon, then as long as negative pi over 2 minus x is greater than 0 and less than delta, then sine of pi plus x minus 1 will be greater than negative epsilon but less than epsilon. And if we're to get an epsilon value that's greater than 2, then we can just pick one of the delta values we used before for an epsilon value that's less than 2, and it will still work. So we've shown for any epsilon value that delta value does exist, thus proving this limit from the left side of sine of pi plus x. We said that's equal to 1. Well, if we do our trig identities again, we see that sine of pi plus x is going to be sine of pi plus times cosine of x. And it's going to be plus cosine of pi plus or times sine of x. And this is 0 times cosine of x. And this is -1. So we get out negative sine of x. So what this lets us know is that the limit as x approaches negative pi over 2 from the left of negative sine of x is equal to 1. Well, based on our constant rule for the limit, we can just pull that right out, multiply it over, and we get the limit as x approaches negative pi over 2 from the left of sine of x rather than negative sine of x is equal to -1. And from the right, it also equals -1. So since those one-sided limits exist and are equal, we can say that the limit as x approaches negative pi over 2 equals -1, which is what we set out to prove before. So now we've shown that this limit is true not only for c values between pi over 2 and negative pi over 2, but we've also shown it to be true for pi over 2 and negative pi over 2. So we can put these equal signs all on there, so we know this equation holds for all those c values. And I forgot to write right here sine of, this should be negative, and because it's coming from the left, sine of x is equal to -1. So now we've shown for all the c values on this interval, which now includes the endpoints, that the limit as x goes to c of sine of x is equal to sine of c. So now we've managed to show that the limit as x approaches c of sine of x does in fact equal sine of c for c values greater than or equal to negative pi over 2 and less than or equal to pi over 2. What we're going to try and do now is extend this to all c values ranging from -infinity to infinity, or all the values on the domain of sine of x. So how are we going to do that? Well, the main way we're going to end up doing it is by using the property of the limit with composite functions. So to start off, we're going to say that m is any integer. So the whole way through this proof, we have to remember that m can be any integer. It can be negative, positive, -1, -2, +1, +2. It can even be 0. So it's allowed to be any integer. And we're going to say that the limit as x goes to c of m pi minus x is equal to m pi minus c. And we know that this is true just based on our limit properties. First, we're going to check the limit as x goes to c of m pi, which is a constant, so it's just going to be m pi. And then we're going to subtract the limit as x goes to c. Because of our subtraction property for limits, we can split it up like that. And the limit as x goes to c of x is just c. So we get m pi minus c as expected. And we can also now say that the limit as u goes to m pi minus c of sine of u is equal to sine of m pi minus c. And this is provided that m pi minus c is less than or equal to pi over 2 and greater than or equal to negative pi over 2. And how do we know that this limit is true, that it exists and it equals that? Well, we just showed that the limit as x goes to c of sine of x is equal to sine of c, provided that c falls in this range. So the limit as u goes to m pi minus c of sine of u will equal sine of m pi minus c, provided that m pi minus c falls in this specific range. That's what we just proved. So based on our limit of composite functions, that property, we can then say that the limit as x goes to c of sine of m pi minus x is equal to sine of m pi minus c. So now, using our properties, our trig properties, specifically with sine, when we have sine of something minus something else, we know we can write that as sine of m pi times cosine of x minus cosine, that should be sine again. So let's fix that. That's going to be sine of x times cosine of m pi. So sine of m pi minus x is equal to this thing right here, but we know sine of m pi, when m is an integer, sine of m pi is going to be something like sine of pi, or sine of negative pi, or sine of 3 pi, sine of 2 pi. That's always 0. So sine of m pi when m is an integer is always 0. So we get 0 times cosine of x. Now this is where it gets a bit tricky. This is where it starts depending on if m is even or m is odd. If m is even, then we have minus sine x times cosine of m pi when m is even, something like cosine of 2 pi, cosine of 0, cosine of negative 2 pi, and so on. And that just happens to be 1. And we get that sine of m pi minus x is going to equal negative sine of x. Now on the other hand, when m is odd, that's when we have something like cosine of pi, or cosine of 3 pi, or cosine of negative pi. We get cosine of m pi is negative 1. And then, in that case, sine of m pi minus x is going to equal sine of x. And similarly, if we applied this same identity to sine of m pi minus c, we would see that when m is even, sine of m pi minus c is going to be negative sine of c, and when m is odd, sine of m pi minus c is just going to be sine of c. So using that knowledge, we can then rewrite this limit for when m is even and odd. When m is even, we now know that the limit as x approaches c of sine of m pi minus x, that's what we're rewriting. We just showed that when m is even, that sine of m pi minus x is equal to negative sine of x, and then sine of m pi minus c when m is even is equal to negative sine of c. And when m is odd, the limit as x approaches c, sine of m pi minus x is going to be sine of x, and sine of m pi minus c is going to be sine of c. And in this expression, we can just multiply both sides by negative 1, and because of our constant property, we can multiply this limit by negative 1 and just pull that negative 1 inside. And we see that regardless of if m is even or odd, we've shown that for any integer m, whether it be even or odd, that the limit as x goes to c of sine of x is going to equal sine of c. And this is provided that m pi minus c is greater than or equal to negative pi over 2 and less than or equal to pi over 2. So what's the difference? Why is this important? Don't we have these two same expressions up here? Well, the difference are these inequalities. This expression we showed to be true for when c is greater than or equal to negative pi over 2 or less than or equal to pi over 2. And now using this process right here, we've extended this to the limit being true as the limit as x goes to c of sine of x equals sine of c for any integer m where m pi minus c is greater than or equal to negative pi over 2 is less than or equal to pi over 2. So if we went ahead and solved for c, and this is what we would find, that c has to be less than or equal to pi times, it's going to be less than or equal to pi times 2m plus 1 over 2, and c is going to have to be greater than or equal to 2m minus 1 over 2, this thing times pi. We draw a little dashed line to separate what we're doing. So we can see that now we've shown this limit is true for x approaching c for all values of c that fit this inequality where m can be any integer. So the important thing is that m can now be any integer we want. And for all those values of c, we know that this limit exists. So why don't we look at some examples? For example, when m equals 0. Of course, that's one we want to check out. Well, when m equals 0, we just get c is less than or equal to pi over 2 and greater than or equal to negative pi over 2. So we already knew the limit worked for that. But now we also know the limit works when m equals 1, or c is less than or equal to 3 pi over 2 and greater than or equal to pi over 2. And for when m is equal to 2, when c is going to be greater than or equal to 3 pi over 2 and less than or equal to 5 pi over 2. We even know m can be negative, so we know it works for negative 1. And when m is negative 1, we know c is greater than or equal to negative 3 pi over 2 and is going to be less than or equal to negative pi over 2. And it's also going to go ahead and work for m equaling negative 2, when c is going to be greater than or equal to negative 5 pi over 2 and less than or equal to negative 3 pi over 2. And we can keep doing this forever, finding different ranges of c where this limit still holds. Now here's the important thing. When we go from 0 to 1, you can see there's an overlap of these endpoints, pi over 2 to pi over 2. And if we're to layer them on top of each other, we now see that a c between all the values of negative pi over 2 and 3 pi over 2 work. But then when we look at m equals 1 and m equals 2, there's that another overlap. So these intervals keep on overlapping with each other, effectively allowing us to see that c is going to work for all the values up to infinity. And then as we go on down, we can see there's still that overlap. We get negative pi over 2 and negative pi over 2, and then negative 3 pi over 2 and negative 3 pi over 2. And we can work m all the way down, because remember, m can be any integer all the way down to negative infinity and any integer all the way up to positive infinity. And that effectively allows us to see that c, that value c that the limit is approaching, is able to be any value all the way from negative infinity and all the way up to positive infinity. And that's how you prove that the limit as x approaches c of sine of x is equal to sine of c for all values of c, all the way from negative infinity to positive infinities, or in other words, all values in the domain of sine of x.